Okay. So, of course, once this is done, you definitely are going to submit this. But if we look at our range calculation, this is the same thing. Let me just go out of this, sort of go up to the cloud for me. Let me pull this back. So we have our range calculation. We still, in this particular case, we have 5.5. Last time we had 5.3. So let's go look at the equations of the line here. So, and I say equations of the line, but this is really our analysis. I probably should change this particular title and just look at it as far as analysis goes, or like analysis part 1. But we have our linear fit here. You know what, I'll just call it that. How about precision analysis? I think that looks a lot better. So if we look at our precision analysis here, you'll see that if you go to 0 degrees, we don't necessarily have a linear fit. We just didn't put those equations in here. All we did was look at the percent difference between the measured range and the calculated range. And you can see that we're getting like 0% difference here. If we go down to 10 degrees, you'll see that we have our prediction for our linear fit to be 0.679, and then quadratic fit 0.697, and our measured range is actually coming out to be 0.636. So all of these decimal places we don't need, but you can see the percent difference between the kinematic theory. That's our 0.6 over here. And I probably should do this. Let's do this. Let's increase our decimal place so we can see what's happening there. Okay, maybe I should increase it more. One more will do. So you'll see we have 0.623, and the percent difference between these two, let me see, the kinematic theory and the measurement is pretty low. And the percent difference between the linear fit and the measurement is higher than the aforementioned one. And then our percent difference between the nonlinear fit and the measurement is getting even higher. Kinematic, the percent difference between the kinematic theory and the linear fit is pretty high. And the highest is the percent difference between the kinematic theory and the nonlinear fit. So the one that I would go with would be the percent difference between the kinematic theory and the measurement. So I would use kinematic theory to really help me predict where this ball is going to land. That's my best era. And as we go out, you'll notice that we have 20 degrees. We have our linear fit here. And it's getting a little bit bigger, okay? So if we do our analysis, we already knew that it was about 5.3 to 5.5. That's our percent difference between our kinematic theory and our measurement. Let's see if we can reduce it by using some of these other equations for our percent difference in our linear fit. Well, the percent difference between the linear fit and the measurement is pretty high, and the nonlinear fit and measurement is high still. And the kinematic theory and the linear fit is still high compared to our theory and measurement. And then we have percent difference between kinematic theory and nonlinear fit. And the nonlinear fit, I would definitely use the percent difference between the kinematic theory. I'll use the kinematic theory to predict where my ball is going to land with higher precision than any one of these other things that we're producing. And so I'm going to stop right there. We have 2 more.